Yeah, comes on everyone. Then the last thing that we did was this thing, the time taken for to empty a hemispherical tank. Chalo, are the scams on? Good, let's start off with a problem. So let's say we have a water tank with a hole at the bottom. This area is A. This is a small hole. Area small a. And then here we have a tap. So from here, liquid is falling into the tank. So two things are happening here. Liquid is coming from the tap, and at the same time, the liquid is going out of the hole also. So let's say this is Q meter cube per second. So every second, Q meter cube second of liquid is coming into the tank. H is the height of the tank at any time t. So liquid flows out from a tap. At a rate of Q meter cube per second into an empty container. So the container is initially empty. Find the height of the liquid as function of time t. Just get the equation and leave it. The integration is a little messed up. We can do that later on. If you get the up to integration, that is sufficient.
Sir, but in exam,
Then what are you talking?
like if it comes in exam, then how can we leave to integration
Then you
now?
should ask your max teacher to teach integration. Which exam you're talking about?
Sir, like any test or
Why will they ask? They have to wait till they teach you in max.
okay,
क्या
sir.
doubt एक word? It's like asking why don't they ask questions from modern physics? Because they didn't teach you, right? Why will they ask you? Plot height versus time graph approximately. So if it's a mains level question, they would mostly ask you the height versus time graph. Let's get this. Don't worry about that. Max, I think calculus, so they'll start in another 2-3 months, I suppose. They must have started already differentiation. Let's see how I do this thing. Get me the equation. You get the equation. Hmax you can find. That was the easy one actually. Get me the answer for B and C. Get me the answer for B. For A, if you can get an equation, that's sufficient. See. So after time t, always, whenever you're integrating, you always have to take a situation after time t. So after time t, let the height of the liquid be x. Right? So in time dt, let liquid level rise by dx. So in a small time dt, this liquid level goes up by dx. So where are you getting this thing from? Two things. One, there is an inflow q meter cube per second. This is the liquid that is entering. At the same time, from the hole, the liquid is going out with the speed of root 2 gx at that instant. So the total volume per second that is entering the container must be equal to the inflow per second. So how much liquid net in the container is inflow per second minus outflow per second? Is that making sense? Let's say every second if 10 centimeter cube enters and every second 7 centimeter cube leaves, the difference must be stuck in the container only. This is outflow per second. So how much is net inflow? So this is your net volume per second in the container. This will be A dx by dt because that is the liquid that increased. What is the inflow? Q meter cube per second. What is the outflow? A into V. Please check your equation. If you got this, physics part is done. A dx by dt is equal to Q into minus A into root 2 gx. Then bring all the extra terms one side. This will be Q by A into root 2 gx is equal to 1 by A dt. So this we integrate from 0 to x and 0 to t. And how do we integrate this thing? But have a look at this equation once. So you want to integrate this. You will learn this in max. We use something called integration by substitution. Q minus A into root 2 gx 0 to x. So what we do, put 2gx is equal to z square. Then if you differentiate on both sides, this will be 2g dx is equal to 2z dz. So dx becomes z dz by g, and the denominator becomes q minus az. You get something of this sort. This can be written as, you can split this. That's what I said. This is a technique in max you will learn. This can be written as q multiply and divide by a. So minus 1 by ag. This can be written as minus az plus q minus q by q minus az. This is minus 1 by ag integral. This can be written as 1 minus q by q minus az. This you know how to integrate. Minus 1 by ag, this will be z minus of 1 by a. That will be minus q integral dz by q minus az. this will become Q by A ln Q minus AZ. I will leave it to you. You can keep going on. Then we have to simplify and all that. But this is the technique we use. So don't worry about the mathematics part. Happy. If they come in the exam, you'll go and talk to your maths teacher. Sir, why didn't you teach this? You fight with them, not with the physics teacher. Clear. So anyway, that is how you can find that stuff by solving. Now, what is the second part of the equation? How do you find the maximum height? Think about this. Initially, inflow must be greater than outflow. So more liquid is coming in, less liquid is going out. Right? So when will you get maximum height? At maximum height, meaning the height is not increasing anymore. Why is the height not increasing anymore? Because whatever liquid is coming must be going out. So inflow per second must be equal to outflow per second. So basically dx by dt is 0. What is the inflow per second? Q. What is the outflow per second? A into root 2 gx. So there you'll get it directly from here. So Q square is equal to A square 2g, and this would be your H max. This is your max height. And how will the graph look like? One thing is clear. The graph doesn't look like a straight line. If you try to plot x versus time graph, initially the height was 0. One thing is clear. As the time passes, it will increase, and it becomes constant. So the graph would look something like this. This is your max height. So the function would be an increasing function and then becomes constant. Clear with the graph? Please have a look at this equation. Like I said, this is the main equation there. If you got this, then the job's done. All clear with this? Next thing. Any doubts on this? So the integration part, don't worry too much about this. This is still very complex actually. There's one z here and there's one in the log also. So they need to give you values. Numbers are given, so it is still a little manageable, but with variables, it looks like a mess. Next one, let's say we have a bowl here. This is not a hemispherical bowl. So this is some kind of a bowl. It is filled with liquid. At the bottom, there is a small hole. Area A. So the liquid started leaking out from the hole. And it is observed when this liquid is leaking out, the liquid surface is actually coming down with a constant speed u. Now, normally think about this. When you take a container and make a hole, if the height is more, initial liquid will go out faster. And as the time passes, liquid will go out slower. That means the height of the liquid will first increase, decrease faster, and then will slowly come down. But here we observe the liquid is coming down with a constant speed. So this does not happen for any shape of a container. It is observed when liquid leaks. The liquid level drops with a constant speed u. So that means I want you to find, so this shape which is there, find the equation of this bowl. Find the equation of the shape of the bowl. So this kind of question, normally they'll ask you like this. They'll say y is proportional to x power n. Find n. That would be an integer question in this. So that bowl ka shape will look like y is equal to x power n. Find n. I hope you're getting it. If you take a rectangular container and if you make a hole, you will observe liquid will drop pretty fast and then it slows down. But here you're saying the container is in such a way the liquid is always coming down with a constant speed. And this happens for a particular shape. So what is that shape? Right, Arya. Try. It's an easy one. You actually don't need any integration. It just looks scary. That might be right, Arya. Let's see. Others. Let's see. Right, Samyak. Okay. So what is the catch in this? So let the liquid be up to some point here. So let's take this bottommost point as origin 0, 0, and let this point be x, y. So in small time dt, let some liquid leak out. So then what will happen? The height will decrease by dy. In time dt, liquid level decreases by dy. So at the same time, the liquid which is leaking out is coming out with a speed v is equal to root over 2gy. So liquid level that decreased must be how much? A into dx, so volume that flowed out. Volume decrease must be equal to the volume that flowed out through the hole. How much did the volume decrease? Now remember, that thing would be like a disk whose radius was x and whose width was dy. So volume that decreased is pi x square dy. And how much did the volume flow out? Area of the hole into velocity into dt. So this would be pi x square, and this will be dy by dt, which is a into root 2 gx. But what is dy by dt? Dy by dt is nothing but the speed of this liquid. If this liquid is coming down with u, the u is nothing but dy by dt. Technically, you get a minus sign there, and this also will be minus sign because it is decreasing. So this guy would become pi x square u. This is a into root 2 g y. Sorry, this is root 2 g y. Square on both sides. This will be pi square x power 4 u square is equal to a square 2g y. So there, you're done. So we get y is equal to pi square u square by 2a square g into x power 4. This is not a parabola. Be careful. Every time it won't be a parabola there. So this bowl is the shape of x power 4. Right, Utsa. Right, Anita. Yeah, most of you got it. So Arya says these kind of bowls are used in Greece to measure time. Interesting. Super parabola. I don't know what this is called. This is not a parabola. All clear with this? Again, if you see not tough to solve, there is no calculus, nothing involved. You just have to write that equation. And that is always the story in this kind of things. Volume outflow is equal to volume entry through the hole, and you finish it off. All got this. Yeah, that's a bit of this. Then, so that's about velocity of flux. Next thing is Magnus effect. So what is this Magnus effect? Now we know the Bernoulli's equation, P plus rho g h half rho v square is equal to constant. Now, if you consider 2 points at the same height, right, then your equation becomes P plus half rho v square is equal to constant. Right, so that means you can clearly see here, if your speed is more, the pressure actually decreases. Now be careful here, huh? People confuse this with something else. People think if a liquid is going faster, shouldn't it collide more with the surface and then you shouldn't get more pressure? Now, don't get confused with the water jet question. In case of a water jet, the liquid was going and hitting a wall and stopping, and that exerts the pressure on the wall. But this is not that way. Think of this, what is happening. Let's say we have a liquid which is flowing in a container, and let's say the liquid is flowing slowly. Now the pressure comes because of the molecular collision. So these molecules which are going, they will collide, 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 collide. That means because the liquid is going slowly, you get more collisions per second. This is not the pressure because the liquid is hitting the floor. When the liquid is flowing, the surrounding, the surface whiches are there, the molecules are continuously colliding them. So there are more collisions per second. So you get more pressure. But imagine the same thing if the liquid is going faster. You're getting it? The liquid is flowing this way only. So some of the molecules are just hitting the surface and they're bouncing. Now what happens if you're going faster? You'll have less collisions. So if you remember how you get pressure, when you put a body in a fluid, the molecules collide with the surface, and that force per unit area is called pressure. Now, don't get confused with this. Suppose if you have a water jet going with speed v, the water jet hits the wall and stops. Then the pressure is force, which is rho a v square by area. So here, if you increase the speed more, then the water jet will hit the wall hard, and then you'll get more pressure. But look at this scenario. The liquid is not stopping. The liquid is just flowing in the pipe. So the liquid is simply going in a straight line. But the molecules which are going, understand one thing, the molecules don't go in a straight line. The molecules are just going, in a random motion. They're going in every direction. So in this process, they'll keep colliding with the wall continuously. Are you getting the difference? So this is the pressure in the surrounding area. It is not the pressure due to the water jet on the wall. So that is the word here. The pressure in the surrounding decreases. And common phenomena, you see this a lot. So that means if you take a pipe like this, where the area is actually becoming like this, you will notice the streamlines are shrinking. So if you choose this as 0.1 and if you choose this as 0.2, we can clearly see V2 is greater than V1. So therefore pressure at P2 will be less than P1. So this part of the tube, right, will experience less pressure compared to that the wider region there. So whenever a liquid flows faster, the pressure in the surrounding region drops. I hope this is clear. You're not stopping the liquid. Huh? Don't put your hand and block the liquid. If you block the liquid with your hand, then more velocity, more pressure. This is liquid is just going away and the surroundings are getting affected because of this. And you must have seen this a lot. Huh? A lot of examples happen. Listen to this. One of the best examples is your calendar. Ever seen the calendar on the wall? We have the wall here and we have the fan here. Now, when you switch on the fan, technically speaking, the wind is blowing. So we think like, because of the wind, the calendar should just stick to the wall. But what do you notice? You will notice the calendar actually flies. Isn't it? The calendar goes up. Noticed it? The calendar is just going towards the fan axle. The reason is same. If you look at this 0.1 here and if you look at 0.2 here, the speed of the wind V2 is greater than V1. So pressure at P1 is greater than P2. So the calendar is being pushed up. Same thing. If you see, right, normally during a storm or something, and if there is a hut or something, the wind is flowing fast. So here the speed is high. So if you take this point as 2 and this point as 1, again, same thing story happens here. V2 is greater than V1. Therefore, pressure inside the house becomes greater than pressure outside. The hut blows off. So even when you design the race cars, right, the same thing happens there. So imagine this thing, you're designing a car. I know that looks weird. It's like some kind of mouse or something. Okay, let's say someone designed a car like this. Now, when the wind is coming and hitting here, the wind will split. So wind is going below the car and wind is going up the car. This is V2 and this is V1. Can you tell me, is V1 greater than V2 or V2 greater than V1? So when you design the car, right, you can change the front part of the car in such a way you can change the wind speed above and below. So you tell me, which one should be greater? Should you let the wind go faster above the car or below the car? And obviously, we should know why. So let me ask you this question. You want the car to fly or go on the road? That is the first question you need to ask. You want the car to go on the road. That means the pressure should push the car down. So this is P2, this is P1. So you want P2 to be greater than P1. Therefore, V2 must be less than V1. So what happens is you make sure the wind below the car is faster than the wind above the car. Then the pressure at the bottom of the car will be less and pressure outside will be more. Because of this, what will happen? The car is being pushed into the floor actually. And because of that, the normal reaction will increase. You get more friction. You get actually more traction. You're getting it? By chance, when the car is going due to some design fault or something, if V1 and V2 become reverse, P1 becomes greater than P2, the car will fly off. And regular cars, it generally doesn't fly off. But the sports cars, right, they can reach speeds of 250 to 80 kilometers per hour. When your plane is taking off, what is the speed generally? When you're sitting in the plane during the takeoff, you reach speeds of around 180 to 200 kilometers per hour. So that is a jerk you feel that actually. So sports cars are different. Your regular roadside cars will never do this thing. Mumbai mein to chance hi nahi hai, so you're safe. Your speed won't even cross 40. Right?
Sir, like, is this why they have low ground clearance or something to reduce cross-sectional area?
Hey, matlab they design that way. You have to make sure you don't want to make it flat also. Then you'll get more air drag. It is a fight between two things. You try to make the surface, See, if you're changing the speed here, that means you're slowing down one side, isn't it? That will create
Yes.
a drag. If you have drag, you will lose efficiency. But if you don't create that difference, you will get this pressure car problem. So they have to compromise on something. And not only that, when the wind is going from the back, now if you see PJ also, na, some cars they have this kind of things, flaps kind of thing. I don't know what they're called. So
Spoilers.
so basically, what happens when the wind is flowing, right? If you ever seen when a plane is landing, at the tip of the wings, you get this currents like this. You get that swirls. Remember, I told you irrotational fluid. Karke? I gave you the picture like this. So the edges of the car, right? Something like this will happen. Same thing happens with the planes also. This will create some kind of, the backward drag. Again, like I said, right, these are very difficult to study theoretically. You have to literally put the car ka thing in a, that chamber, and then you have to study how it flows. Meaning you can keep going with more examples. What is a heart attack actually? Ever thought about this? People say that someone got a heart attack. What exactly happened? So what happens in a heart attack, right? You have a blocked artery. Now, this is another common mistake. What people think. People think fat got deposited here, so you can just clear it out. Unfortunately, whenever you have this artery, right, the blockage actually happens on the inner vessel. The fat gets deposited inside. You getting how it is? So you just can't push it. Getting it? Our normal imagination is this. We think there is a vessel, a pipe kind of thing, and this thing got blocked. That is some kind of blockage. Now, because see what happens with the blockage, the liquid, the blood which is flowing, will start getting compressed here. So if you choose the 2 points here, 1 and 2, V2 becomes greater than V1. A1 V1 is equal to A2 V2. Therefore, pressure at P2 becomes less than P1. Now, you know what most people think? If there is a blockage, they think the artery will burst. It doesn't burst, something else happens. Now, if you look at this point here, now here the pressure is P2 and outside the pressure is P0. And P0 is greater than P2. This artery is actually being compressed from outside. It is being pinched. And then once the pressure becomes strong enough, this entire artery will collapse. It just collapses. And the blood flow completely stops. If this happens in the coronary artery, which supplies blood to the heart, we call it a heart attack. Right? And it doesn't happen suddenly. It takes years of, messing up everything. It implodes basically. It does not explode. That is the reason. Think about this thing. Whenever after the surgery, right, what they do, they put a stent. Kabhi suna? They put a stent. Where do you keep the stent? They don't keep it outside. If it is going to explode, shouldn't you keep it outside? They actually keep it inside. It is to support the walls of the artery from not collapsing. Clear with this? If you had some kind of clots and all, they can be pushed away. But if there is a fat deposits, most of the times they're inside the walls. So same thing, we can play more. Let's say if you have a ball here, and let's say if it is going with V, and if you give a spin omega. Now, if you look at the ball here, the topmost point will have a speed of V plus R omega. The bottommost point will have a speed of V minus R omega. Same story. You have more pressure here, so this is P1 and this is P2. So P2 becomes greater than P1. So this ball will get an upward lift. So if you ever played football, you must have noticed that you kick the ball, sometimes it goes over the goalpost. So spin matters. Did you know about this thing? There's something called a banana shot. If you are watching football, you must have heard about it. There is something called a banana shot. Never heard about it. It's like this. Top view. Huh? If you're looking this from the top view, let's say this is that football goal post, right? Normally, if you see that penalty kick and all, right, people are standing in front of the goal post, and this guy has to hit the ball through them. So one of the most famous shot is this. You hit the ball like this. It actually turns in the middle and then goes into the goal post. The ball literally curves. This thing gives you a shape of a banana. It's called a banana shot. Never heard about it? So the idea behind this thing, right? Here you do something little different though. You take the ball, you give the spin this way, omega, and you give the velocity this way. That means you have to kick the ball not in the center, you have to kick the ball little to the right. Now what happens? See, when the ball is going like this point will have a speed of v plus r omega. This point will have a speed of v minus r omega. Right? So that means you should actually hit the other way around. So this will be v minus r omega. This will be v plus r omega. So here the pressure will be P1 and P2, and P1 will be greater than P2. So the ball is trying to go this way, straight line, but the force is pushing you this way. So the ball, as it is going here, will start turning inside. It really turns a lot. Meaning, generally Brazilians, right? They're very good at this. I'll show you something. So this shot is called a banana shot, especially in the penalty kick, right? I think Ronaldo, right? He does it really well. Most of the footballers does it well. You need a lot of practice. But that is the main concept behind this. So this is what I'm saying. The coach will know all this stuff. The player need not know all these things. Robert Carlos, that guy is the... There is some video also of his 10 of his best shots. So that is one. And if you ever seen an ant nest, did you ever observe this ant nest? They make a hill on top of this thing. If you ever go and break that nest, you will find there are no ants inside. Did you ever notice that? When I was a kid, I used to do a lot of nonsense like that. So these things just used to build a nest. I used to go destroy them. And by evening, they used to build it again. And the surprising thing, right? You'll find very little amount of ants there. So what? It is like some people are living in high rises or something like that. I used to think that way, but it's not that. And right, this is called actually a wind tower. This concept, right? They also, in our old buildings now, when people used to construct, they used to use this. So this is the idea behind it. They construct a wind tower like this, right? So the nest is actually something like, a very small entrance here. Again, I'm just drawing a simple version here, but the entire nest, if you see, it is pretty complex. Like, you have a lot of chambers and everything. And there is one exit also somewhere far off. There will be one exit somewhere also. Now look at the problem here. If you don't create proper ventilation, ants end of the day still breathe in oxygen and breathe out carbon dioxide. So the carbon dioxide is heavier than air. So this entire nest will get filled with carbon dioxide and they'll suffocate and die. Clear with this thing. That is the reason we don't build offices and, houses under the ground. You need to have a constant ventilation. If you ever been to, this underground, kabhi dekha, underground shopping malls. There is one in CST also. It's an underground thing, right? Or if you ever been to any abroad also, shopping malls, when they build it under the ground, or for metros also, for example, if you go to underground metro station next time, observe that. You will find a lot of vents and there's a lot of ventilation air is being pushed inside forcefully. Right? You stop that, the whole thing will get filled with carbon dioxide. And this is the same reason, imagine you're going somewhere and you found a big cave. You're not supposed to enter the cave just like that. Especially when the cave is going under the ground. If it is going deep, first thing you're not supposed to go. What generally happens, right? People without doing proper research, they go inside and the whole thing is filled with carbon dioxide. And carbon dioxide is not poisonous. You breathe in more and more carbon dioxide. The carbon dioxide is getting dissolved in the blood. So the oxygen levels keep dropping. Now, unfortunately, your brain can't tell the difference. So first thing that will happen, you'll faint, you'll just fall down and you'll die. That's it. You will just faint. Nothing happened. You'll just faint. Now, if someone does not pull you out suddenly, then you're gone inside. And people think like, there is a ghost inside the cave. That's where you started. And you feel like, all the symptoms will come. It feels as if someone is sitting on your, chest. Your body feels very heavy. Your lungs become very tight and your blood is, body is struggling to get more oxygen. And same way, if you have an abandoned well, you're not supposed to get into the well. Getting it? Because again, same story. If it's an abandoned well, the entire bottom part must have been filled with carbon dioxide and carbon monoxide. And so what they do, they actually take a stick or something, they put fire and they drop the thing inside. If there's a full of carbon dioxide, it'll get extinguished before reaching the floor. So first you test whether the fire can actually burn at that bottom. If it can burn, means there is an oxygen. Then you can send someone inside. So you have to use special equipment to go into these abandoned wells and these caves. So next time when you go exploring, just don't jump into a cave because you found it. If it is a tourist place, they must have already done research and they must have done ventilation. So there. So don't just enter into any random caves thinking you're exploring. You will get lost, you will suffocate, and gone. Main thing is that, meaning your brain will stop working, right? You don't understand only where you're walking. So what is the idea here? So when you build a little tower like this, generally, the higher you are, the wind actually flows little faster. Different reasons. If you're living above 10th floor or 15th floor, you notice this. You open the windows, there's a lot of wind coming. So then the wind is blowing here. So speed is more. So this is P1. So here at this bottom point, the pressure is P0, right? So P0 is greater than P1 because the wind speed is low. So air actually enters from this thing. And this air which enters inside will flush out all the carbon dioxide. So that is actually a wind tower for circulation. The moment you destroy this, that's where the ants go mad. They start building it up immediately because the whole ventilation is stopped. But anyway, ants are smart. They build up, 2 to 3 separate wind tunnels just to be safe. So the deeper the wind tunnel, the deeper the nest, the higher the wind tunnel you have to make. So generally, you can tell how big the ant nest is based on how high they're making the tunnel. Clear with this? And anyway, you make a nest like this. Sometimes snakes go inside and sit, and people think it is a snake house or something. So, there's a festival in Andhra actually. I don't know whether it is there or not. So they go to this snake thing. They put all eggs and milk here, and they pray to the snake and all. Is there any festival like that here? No, no. Andhra, mein, there is a festival like that. Getting it? So they all go there, and unfortunately, by chance, if a snake comes out, everyone runs away from there. So I never understood the logic behind it. Like, right? You say you guys are going and praying, but if it comes out, you run away. One. Second thing, and the amount of milk and eggs they put into the nest, if really there is a snake, it will flood and die. Getting it? So I never understood the madness of it. So people, I was happy. Nagdev Puja, so they call it something like that. So I never understood the logic behind it. So some people became very smart. They understood people are anyway going to put all eggs and all. So before the festival happens, 1 week before, they go and build nests. Getting it? They build nests. At the bottom, they put all the stuff. So when people come put all the eggs and all, you can collect all the eggs. And next day in the market, they sell off all these eggs. That's the one good business actually. I think nowadays they stopped it a bit. But people used to do all kind of nonsense. I never understood the logic, but I was happy because I was getting a holiday. So I said, okay. If you're giving me a holiday, I'll celebrate any festival. We will even celebrate mosquito ko birthday also if you're going to give us a holiday in school. So that way. Next thing, an aeroplane wing. Worst thing, right? They used to put sugarcane inside the nest for an snake to eat. I feel like people were weird. And if you say anything against them, they're like, "Oh, you don't believe in God." That this. I said, "Yeah, there should be some logic." So, how do you make an aeroplane wing? Again, not exactly like this. Just a design there. So again, it is designed in such a way the wind flow, right? The speeds are different on both the sides, V1 and V2. And here the pressure is P1 and P2. Now, if you use the Bernoulli's equation, P1 plus half rho V1 square, P2 plus half rho V2 square. So the difference in pressure, P2 minus P1 is equal to half rho V1 square minus V2 square. So the thrust force on the aeroplane wing, P2 minus P1. So this is what actually happens on a plane wing generally. You create a difference in speed and that gives you a thrust into area of the wings. That means this is half rho air V1 square minus V2 square into area. That's your upward thrust. Clear with this. So if you actually see from this equation, right, if you have a submarine which is going under the water, instead of rho air, you get rho water. So a submarine can generate more thrust, right, with a slow speed because the water is more denser than air. Yeah, but again, vice versa. You also have more viscous force and all that stuff. There's a more of theory and all this technically. So let me show you something. So that is your Antka nest. That's almost height of 4 to 5 inches. So what this guy is doing, he's putting molten aluminum inside. Yeah, unfortunately, evil thing, but for the see the nest. That thing he must have. That's almost 400, 300 degrees ka thing. He's just pouring molten aluminum, so it's going in. Yeah, the poor thing, the nest is dead. So then you wait for it to cool down, then you gently remove all that sand. These are not the nests in India. You don't get nests like this in India. In India, if you see, the ants are actually pretty cute and innocent. They will just come and eat your food and they'll bite you a bit, but they don't kill you. The most dangerous ants, right, are there in UK side and in Africa. In Africa, there's a certain kind of ants. These things are they move in swarms. Matlab, that one colony has around like a billion ants. And when these things come, right, literally the streets are filled with ants. And when they come, people literally evacuate the villages, they go away and they come next day. Anything that is left over, they will eat. Anything. Matlab, by the time these people come back, all spiders, lizards, mouse, rat, everything is gone. Right? By chance you forgot to take your cow there, your cow is gone. Human stays back, human is gone. They literally eat everything. Right? So there is what that is a one dangerous kind of species there. These are just they'll just eat everything in the flow. You can't do anything. They're huge. Right? So now you're removing that sand carefully. There you get that big chunk. And he sprays water, cleans it, polishes it, and this is the final piece. Huh? You can actually put this in a nice design thing. Can you see that shape? That is how an Antarctica nest looks. So complex. So at the top, you just see a small hill kind of thing, but underground, this is the nest actually. But nice art piece, no? You can actually put it and sell it also. People will buy. Then you can Nietzsche, you can write Antarctica grave, something like that. The death colony or something. So this is a small version. So this is a bigger version. They're doing the same thing, but this time they're pouring concrete. So this is one of the biggest nests in Africa. And look at the amount of concrete they're pouring in.
The amount of cement required is extraordinary. For 3 days, they kept pouring until 10 tons of cement.
They poured 10 tons of cement into that.
They begin the export.
Then they started digging. Now think what happens, huh? So in the Antarctica nest, everything cavities, right? They're filled with cement now, so everything will solidify. So the Antarctica nest will look like this bobs of cement and concrete. They brought a crane also to dig. That is the size of an ant nest.
At last, they begin to see that there are payments.
Can you see this thing? That's your Antarctica nest actually. So each thing compartment you can see. And you can see the pipes there. That is the Antarctica, the paths. They literally built a full colony there. Like
of the main routes and leads.
The total height is 2 floors.
Are designed to ensure good ventilation and provide a single mine. But this gated the super.
It's a super ant colony.
And goes 8 meters into the earth.
8 meters deep.
In its construction, the colony moved 40 tons of soil. Billions of antloads of soil were for human terms was carried a kilometer to the surface. Building the group.
I'll post that in the group. You guys can check it out. Then look at this. This thing comes in the beginning only. See that scene again. So see, he's kicking the ball. See how it bends. Did you see how the ball bent? See that again. So that's what I call as a banana shot. So this is a video they teach you how to hit the banana shot. We don't need that. So this video doesn't have a good clarity actually. So this is about Robert Carlos. So this is the guy, 73. I don't know if you can see this clearly, but so there are people standing in front of this, the standard stuff. So there he's coming to hit. Now from the side view, it doesn't look like it went like straight, but if you see it in slow motion, did you see how he kicked? The ball is going to the right, 137 kilometers per hour. I'm pausing it. Now see where is the ball? The ball is gone to the side. Again, I'm pausing. So the ball is literally going to the right. Set almost you can see near the goal post. Then it started blurring actually. It got blurred actually. The ball then took the turn and went inside. There. So they're teaching you how to hit the ball. You hit on the left corner for it to turn. So there they use it in football. Then look at this thing.
Recently, some friends of mine went to the Gordon Dam in Tasmania for 450 a basketball.
So they're throwing a basketball. Now see what happens. First thing, you're just throwing the ball. You're dropping it without any spin. So if you drop the ball, it almost just falls straight. Nothing happens.
But it lands right below where it was.
So it almost fell straight. But if you give a little spin,
This time, it's a backspin. Oh, where did I go?
the ball just starts gliding. See, just to zoom out, did you see how far it went? Again, what happened when you gave spin? The speed on both the sides became different. The difference in pressure started pushing it forward. The ball actually traveled forward.
I literally just dropped it with a bit of spin. Like I didn't even throw it, and it just took off. Like we had no idea that was going to do that. Instead of getting deflected, didn't it?
So that is there. There. This is I was saying. This is what they do. They put it in a wind tunnel and they release smoke and that see, how this is all streamlines basically. You can see clearly the streamlines. Now you're increasing the wind speed. So you can literally see how the wind behaves, about each part and then you design it. This is the bind force. You're putting water. You're putting salt. By adding salt, what are you doing? You're increasing the density of the water. You took an egg, sank. Took an egg, salt water, floats. Because the liquid is more denser, it floats. That's the reason you don't sink in the, what do you call it? The Dead Sea. Remember the force of a water jet, rho a v square? This, if you go to Dubai, you can do this. So look at that thing. So each water jet is pushing out water. You get a force of rho a v square. It's like rocket proportional indirectly. There. That is one. This, you guys will like it. Did you see how the car flew off? This is what I was saying. If your difference in speeds are not proper, the cars will fly off like this. I hope the driver is safe. This you can see more clearly. The car literally lifts off the ground. Look at this thing, huh? Did you see how did the car got off? It just flew off. Look at that thing like an aeroplane, huh? It just took off. There. Jesus, right? So there, that is what happens with the cars that fly off. So, and this is just a three-quarters dam actually. I don't know why do I have this. That just show the dam. This is the China three-quarters dam. Huge actually. Generates almost 7% of power of China.
So they told that it can like slow Earth's
Yeah, right?
rotation. How do they do it?
What they do it?
Like it's told in the video that they slow the Earth's rotation.
No, वो just
वो
they
कैसे
built
करता
it
है?
and it messed. They don't do it like that. It changes the Earth rotation by 0.003 milliseconds. ऐसा कुछ तो है. It's a very small amount, but it does affect.
मतलब कैसे हुआ उसने मोमेंट ऑफ इनर्शिया को बढ़ा दिया
No,
इसलिए?
you just messed up the moment of inertia. You are storing so much water in one place, right? You messed up the moment of inertia.
Oh,
But it is not like so much that your literally day becomes 24 hours or 23 hours. That would have been interesting, but it just barely changes by a microsecond, so it's not much.
China
There's
will
all
blackmail
exaggeration
us.
there.
Will not give you
ऐसा
one
कुछ
extra
नहीं.
hour.
Uh, it's like if you go and destroy the Mount Everest, so even then you can change Omega. But just give the Mount Everest to developers and tell them you can build apartments there. They will destroy it for you in 2 years. People are capable of that. आ जाएगा Godrej का property, all this big builders will go and build it. Adani को दे देना चाहिए. Adani Himalayas done. They will remove that entire Himalayas in 2 years. They'll dig it up completely. Then also we can change Omega of the Earth. So things like that. Okay, so that's a little bit about aeroplane wing. Like I said, there are no problems. It's all theoretical stuff only. Right? Take a break. Come back in 5 minutes. We'll continue from here. Oh yeah, got something.
Sir, I didn't understand the velocity different, like aeroplane wings.
Hmm. Why is the speed different? That you're asking, or
Mm,
no? They design the thing like this. Normally, when they design, this side is you want the speed way to be more. We want to be more, na? So this will be more smooth, and this will be more rough kind of thing. So when this is gliding here, the wind will go faster here. Here, the wind will get obstructed more. So speed changes because of that. So you have to design the shape like that. Automatically speed change नहीं होगा. Getting it? So you make on the top something like more smoother surface, and here you make it more rougher kind of thing. So here it will get blocked more, na? So speed कम पड़ेगा.
Then, sir, if V2 is less than V1, then P2 will be greater than V1.
Which should be
Then
more.
it
You
would
want P2 should be greater, na? You want the pressure from the bottom to be more, ना? आपको ऊपर जाना है.
okay, हाँ, okay. So,
ना? P2 is greater than P1, so V2 will be less than V1. So the wind above
okay.
the wing is going faster than the wind below the wing. कार में रिवर्स होना चाहिए ना. कार में you don't want it to fly. तो उसमें P1 is greater than P2.
ठीक.
हाँ.
Thank you, sir.
Sure, let's start off. The next thing. So in the race car, due to which conditions P2 becomes greater than P1? So same thing, right? In the race car, right? You have to make sure you have to design the car in such a way. You want the pressure on the top should be more because you want the car to be pushed down. So velocity has to be less than this. So the wind which is going up should be flowing slower, and the wind at the bottom must be going faster. That means when you design the car, you make sure the upper part is like little more. Think of like this. I know that's a bad idea, but still, you can clearly see the wind which is hitting here. This goes very smoothly, but this thing is getting obstructed here. So that is how you mess up the speeds. That's a bad design. Don't design anything like that. If you ever seen this, this bullet trains, Japan ka, you can see the nose how it is designed. It's based on that. Next thing, we have Venturi meter. Now, these are all concepts. Do you guys know how does your gas cup meter work in your house? How does the meter know how much gas did you consume? Or if you're in Delhi or somewhere, right, then they have something called water meters. Right, Mumbai, we don't have water meters. We just pay a certain fixed amount to the BMC and they just charge you based on the society. But technically, the US and abroad, when you go, right, they charge you even for the water that you use. You have a separate bill for electricity, water bill, and gas ka bill, whatever. So this is what we use. I'll show you two things. First is your regular one, and then I'll show you the actual things they use. So this is called Venturi meter. So it is useful to measure the volume per second in a pipe. So the theory is the question itself. And if you're in HSC board, 12th standard mate is there for 12th boards. So case one, the open type. So the design goes like this. So there. So we have two vertical projections from here and the liquid is flowing inside. So as the liquid is flowing here, the water level, if you see here, so in this thing, there'll be some liquid level here. In this thing, the liquid level will be something like this. Let this area be A1. Let the pressure be P1. Let the velocity be V1. Right, and this height of the liquid here, let it be H1. Here, this is V2, the pressure is P2, area is A2. And let this height be here, H2. Pretty straightforward. Remember, we have only two equations with you. Remember, equation of continuity and Bernoulli's equation. That's it. So first thing, equation of continuity, A1 V1 is equal to A2 V2. Then when you use the Bernoulli equation, P1, height is same. You're doing between 1 and 2, half rho V1 square is equal to P2 plus half rho V2 square. This is equation 2. And we also know P1 will be P0 plus rho G H1 because the liquid in the vertical cylinder is constant. And P2 will be P0 plus rho G H2. Substitute everything here. P0 plus rho G H1 plus half rho V1 square. P0 plus rho G H2 plus half rho V2 square. P0 will cancel. This will be G into H1 minus H2. is equal to half into V2 square minus what is V1 square? V1 square is A2 square. V2 square by A1 square. So from here you can find V2. This will be root over 2G H1 minus H2 by 1 minus A2 square by A1 square. If you remember, this kind of looks like velocity of efflux, isn't it? Kind of, it looks like that. So this will be root 2G delta H. That's the difference in height between the two vertical cylinders. 1 minus A2 square by A1 square. If you see this, you know everything here. You know delta H, which you can see from the observations. You know A2 and you know A1. So the liquid that is flowing per second is area into velocity, which is A2 V2. So this is one technique. Nice one. Got something? Yeah. But this is a bad model, right? Because if you can see, these are exposed to atmosphere. So if you are measuring gas or something, they can leak. And we don't want to have something like this. So we want to keep a closed type venturimeter. So olden times, this is one of the technique actually, right? To figure out if there's any underground water or something like this. Think of like this. Imagine you have an underground river. So the river, right? Underground river, some points it is broad and some points it is thin. Now you tell me, if I dig a well here and if I dig a well here, in which well will you get more water? You know, how does actually water, people say underground water table. Ever heard that term, water table? How do you think water is there inside the ground? When I was a kid and I used to think like this. I used to think the ground is there. Inside the water is like this, like a pocket. You put a straw kind of thing and you pull out the water like a coconut. That's what I used to think. It doesn't work like that. How does water look inside? Think of this thing. Take a sponge and put it in the water. The entire sponge absorbs water. Now, if you see, there is water inside the sponge, but it's not in one location. It is spread over everywhere. So what happens, right, when you dig an underground well? So when you're drilling the well, what you're doing is you're literally, there are so small mini, water flows inside actually, the streams. The entire thing is filled with water. So when you're drilling a well, you're literally breaking the streams and you're collecting all this water. So all this water which gets collected, you're pulling it out continuously. It is like you're drying out that sponge. Now imagine what happens if you start pulling out more and more and more water. As you pull out more water, the entire area becomes dry and it crumples and you get sinkholes. Did you ever hear this in Bangkok? That entire area suddenly sank into the ground. Do you ever hear these kind of things? This is what happens when you remove all the water from the underground water. Getting it? And normally, right, you have a rule actually. For household purposes, you're not supposed to dig the well more than 100 feet. So when I was in school, we didn't have this municipal water and all. We used to have a bore well. From there, we used to get the water. So initially, it was 100 feet. Then as new and new society started coming up, right, people realized 100 feet was not sufficient. So people started drilling more. Now see what happens. If your neighbor drills a hole deeper than yours, then what will happen? If you don't have enough water, all these wells will start going here. So your water in your bore well will start drying up. So what you have to do, you have to go and drill it even more. Now it becomes a competition in that area. Whoever has a deeper well will get more water. And eventually you'll mess up the entire water table in that area. The government came with a regulation of 100 feet, but yeah, people still mess it up. So I think almost a decade back, I heard in Hyderabad, there's a huge society. They dug up 3,000 feet. 3,000 feet. The entire society is, it's a big complex. It is owned by some politicians, so they just dug up bloody 3,000 feet. And it was so bad. From that well, up to 4 kilometers, the entire area, the water levels dropped. All the bore wells in 4-kilometer area stopped working. I don't know, someone filed a case, there was a court case and all, but not sure what happened exactly. 3,000 feet, you drill those kind of things for oil, not water. But good thing, we didn't get oil. Like, imagine that guy drills a 3,000 feet oil and, you get oil in Hyderabad. Trump would have attacked Hyderabad by now. So in a way, we are safe.
Tariffs.
There is that recently some meme is going on. It's an old meme actually. Like, so there is a plate there and some guy is eating food. Chapati end is there and there is a curry there and thoda oil ज़्यादा गिर गया. There is a meme that I don't know if you have seen that. So it's like the moment you put extra oil in the curry, Trump will come and attack your curry. It's like that. So don't put too much oil in your curries. So people are joking now. Anyways, you must have heard, right? He went to Venezuela and he just kidnapped the president there. So not him exactly, but yeah. Trump wouldn't have even walked 10 steps. He would have fallen down on his own. Case 2. Close type. So this is called a manometer is connected. Manometer is, I'll show you what it is. So this is how the setup looks. Now again, I'm drawing a big one, but you have the smaller versions actually. This is what they keep in your gas meters. There. This is how it looks. So this is your manometer there. So here the liquid is flowing, the gas or something. And here you have mercury. So you have two, basically that's a gas and this is a different liquid there. So generally they use mercury here. Right? And this is your raw liquid. So let this difference be H1 and let this difference be H2. Now, because mercury is conducting, right, what you have some detectors here. So when the mercury is coming here, this becomes conducting and the electricity will pass through the detector. So you know what is the level of the mercury inside without actually going inside and seeing. So you do all that small circuitry and all, right? So that is your H2. This is your V1. Pressure is P1. Area is A1. So listen to this carefully. Like I said, this is the question, this is the theory, this is everything. V2, pressure is P2, area is A2. And from here to here, let this height be capital H. Now let's put on all the equations. First thing, equation of continuity. A1 V1 is equal to A2 V2. Next thing, Bernoulli's equation. P1 plus half rho V1 square is P2 plus half rho V2 square. Now, if you choose 2 points here, let's call this thing as A and let's call this thing as B. We can say PA is equal to PB because they're in the same level in the liquid. Now, what is PA here? Now, be careful here. You want to find PA. There are two liquids here. PA will be P1 plus rho liquid G. The difference in height will be H minus H1 plus rho mercury G H1. That must be equal to P2 on the right hand side. Rho liquid G, the difference in height is H minus H2. So basically here, this is the liquid and this is the mercury. So there are two different liquids. Plus rho mercury GH2. Check out that equation. That's your pressure at A and B. Now, if you simplify that, you get P1 plus that capital H term will cancel off. You end up with rho mercury G H1 minus H2. This will be P2 plus rho liquid G. Actually, no, this side only will come. Rho liquid G minus sin H1 minus H2 is equal to P2. So we can get P1 minus P2 is equal to P1 rho and rho G H1 minus H2. Okay. P1 minus P2 will be rho Hg minus rho liquid G H2 minus H1. There, we got a pretty good relation there. But what is P1 minus P2? That will be half rho V2 square minus V1 square rho mercury minus rho liquid G H2 minus H1. And from equation of continuity, you can substitute here. This would be half rho liquid V2 square minus A2 square V2 square by V1 square. Simplify all this, you'll end up with V2, which is root over 2 G delta H rho mercury minus rho liquid by rho liquid 1 minus A2 square by A1 square. That's your velocity V2. And what is the volume flow per second? A2 V2. So what happens in your gas meter every time you switch on your stove? When the stove is switched off, there is no flow. So H1 and H2 will be equal. So delta H is 0. So V2 will be 0. Volume flow is 0. Your gas meter will not work. The moment you switch on your stove, the gas will start flowing. Because of the gas flow, the difference in height H1 and H2 will come. Now, inside the gas meter, you have all these calculations, right? It will calculate V2 value directly from all this stuff. Because see, all this is constant. Rho mercury is constant, rho gas is constant, A2 I know, A1 I know, G I know. I just need to find delta H from the measurements. So if you open all the 3 stoves, if let's say if your stove has like 2 to 3 stoves, and if you switch on everything, more gas will flow out. If there's a more gas is flowing out, you get more delta H. So V2 will be more. You're getting it? So automatically everything is taken care of. If you use more gas, you get more build. So from there you get a V2, and then if you multiply with A2, that gives you the volume of gas flowing out every second. And based on that, the meter runs. And that is how you know end of the month how much gas you consumed. I know it's a little more of an equations. Just have a look at this. If you see, I just played with these things only. Equation of continuity, Bernoulli's equation, and PA is equal to PB. That's it. That solving is lengthy. All got this? That's your third one. If you see in fluid dynamics, the first one was velocity of efflux. Second thing is your aeroplane wing and the Magnus effect. Third thing is your Venturi meter. The fourth one is a siphon. So what's a siphon? Did you ever do this thing like, if you take a pipe, put it in some, water or something, and if you just pull out the air with your mouth and just open it, water starts coming out. People do this thing to steal petrol. Did you ever steal petrol? No, you must not have done that. So, when we were in college now, 11th and 12th standard, one of my friend had a bike. His dad ka bike basically, getting it? So, and we had to go somewhere, so we never used to get enough petrol. So his dad ka bike used to be all full of petrol. So we used to steal petrol from his dad ka bike. Not exactly stealing. So we used to borrow petrol from his dad ka bike. Getting it? So this was one of the technique there. So you put the pipe inside, you just pull out the air, you have to suck the air out from the pipe, and if you just leave it now, petrol comes out. His dad always used to wonder, it used to be full, but the petrol used to get over in 1 week. He never understood why the petrol is getting over. And the best thing, his dad is a circle inspector. So, no, he used to think someone is stealing his petrol from the police station only. He didn't know that in the house only the son is stealing the petrol. Interesting times. So anyway, I used to have it one in the house also. I think this thing when I was in circle inspector is like check karna hai online, you will figure it out. Abhi physics class mein how do we explain police ka ranks? तो Naresh, Hari, any doubts you ask? So you want to know what is a circular inspector? Go to the highway, do a strike, right? Stop all the vehicles, right? If you do that, maybe the sub inspector will come and arrest you. Go and hit a politician, circle inspector will come. So normally, sub inspector is a guy who takes care of one police station. Circle inspector is a guy who takes care of 4 or 5 police stations in an area. Happy? That way. So let's say we have a tank here. So when I was in 5th or 6th standard, I guess, we used to stay in a house there. We didn't have a water supply. Like every day morning, it used to come for 1 hour. Evening, it used to come for 1 hour. So we have to fill the drum. So we have to put all the water in the drum. Now I was too small. Okay, 4th or 5th standard. Now taking water from the drum and taking bath, it was difficult. So we used to have a pipe inside. The drum used to be full of water. So I used to put the bucket. There used to be a pipe inside. My mom taught me this. After that, we used this technique to steal petrol. That's a different story, though. So we used to have a pipe here. So my mom said, like, if you can just put your mouth here and pull the air out, you get a vacuum kind of air. Because of the vacuum, my mom didn't explain the vacuum and stuff. She simply said this. So you just put your mouth there and pull out the water. So once you do that, water starts coming out automatically. Then you fill up the bucket and then put the pipe back inside. Did you guys never did this? Never seen this? Sure. A simpler example is this. When you go to the saloon, remember they use that water spray? That's actually a siphon. Instead of using mouth, you're actually using that mechanism to spray water. So how does this work? So you have a pipe inside. So let's say the height of the liquid is H1. Let's say this opening is H2 and let this thing be H3. What is H1? Height of the liquid from the reference. What is H2? Height of the opening. What is H3? The maximum height of the siphon. Again, a pretty simple concept, like, the formula is there, but you should know how it works. So assume this is a point 1. So liquid from here, this is a streamline. It's flowing through the siphon. Then it flows out. So let this be point 2. And let this be point 3. So point 1 is on the surface and point 2 is just outside the opening. Right, and therefore P1 is equal to P2 is equal to P0 because both are opening there. Now apply Bernoulli between 1 and 2. So the equation would be P1 plus the height is rho g h1 plus half rho v1 square. P2 plus rho g h2 plus half rho v2 square. P1 and P2 will cancel and we'll neglect this half rho v1 square because that area is big. Since A is much greater than A, V1 will be much smaller than V2. So we can ignore that. P1, P2 will cancel. So when you solve this, you end up with V2 is equal to root over 2G into H1 minus H2. Kind of velocity of efflux ka formula, isn't it? I can write here only. V2 is equal to root over 2G H1 minus H2. It's a simple idea there. As long as the height of the liquid is higher than the height of this opening, liquid will keep coming out. Obviously, liquid is happy because it's going to a lower potential energy state. Is that clear, everyone? So how does this work? Have a look at this. Where is this guy?
This is a working siphon.
There, this is what I was saying. Look at
In a
that.
machine, liquid is moving through a hose from one container to another. The forces driving this process are complex and interesting. Let's investigate. Start by setting a cup full of
So
water
there,
on
you
the
kept
bottom.
a cup there on the top and one empty cup. Now, if you put a pipe, nothing happens, right?
And an empty cup on the table. Position a hose so that it connects both cups. I colored the water to make it easier to follow this process. To fill up this, insert a pipe.
Now, what they do now, we're not using mouth and all. He's keeping this pipette. So that bulb, right, you can push the air in and out.
Squeezing the bulb.
So he's putting there and he's pushing the air.
Creating bubbles.
There you're getting, see, bubbles. So all the air from that pipe is removed. So now you're creating a vacuum inside. So when you open this, now the liquid will try to rush in.
Slowly releasing
Now see,
the bulb.
if you release that, liquid comes inside.
The tube. We might say that the pipette is sucking liquid into the tube. Actually, the liquid is being pushed into the tube by the external air pressure.
Because you pushed all the air out, you got a vacuum now. Outside, the atmosphere is pushing the liquid and the liquid is trying to enter this pipette.
When we release,
So this is what you do with the mouth also, actually. When you pull out the air, you're creating a vacuum kind of thing and the atmosphere is pushing in. And then now you gently put it in the lower cup.
the bulb, a partial vacuum appeared. External air pressure pushes water toward this vacuum. To start the siphon, remove the pipette while holding the end of the tube below the level of the liquid.
And then you just leave it there.
Keep this end of the tube below the liquid level, or the liquid will run back into the upper cup.
That's it. Once it starts, the liquid will just keep going.
One of the surprising things about this is that the liquid actually flows uphill as it exits the upper cup. This process requires both air pressure and gravity.
You observe one thing here? When the height of the liquid seen from the ground level, when the heights become same, the liquid will stop flowing. Because there is no reason for the liquid to go to a higher state.
Start position. We see that the column of liquid in the tube on the left.
So you can try to also argue with in terms of force. The pulling force on the right, the red one, is more than the yellow thing, so liquid is coming out. And when they become equal on both the sides, it stops flowing.
Equilibrium has been reached. The level is the same in each cup.
That's what he's saying. If the height becomes same, liquid will stop working.
Liquid weighs more than we can see the siphon starting to flow, stopping when both cups are at the same level.
See? Liquid flows till the heights become same.
There is another question. Why doesn't it break in the middle and flow in two directions before they create it together? Holds air. Dirt. Mixing two colors with a siphon creates some dramatic effects. Blocks. You
can do it multiple levels also. Huh? Look at this thing.
Starting each section of the siphon in sequence.
So he's using siphon, putting there. Then you can create a system like this. The liquid is just continuously jumping from one container to another. You keep pouring liquid on the top, it will maintain.
Go to the site, hylaroad.com. Follow the projects.
There, that is how it is. This is another, just a normal thing.
Let's do time trials for 3 different ways to empty the.
So whenever you want to empty a water bottle, how do you empty that? So this is one way.
Let's do time trials for 3 different ways to empty this bottle.
These are
The
most
first way is
standard
to
way,
do
right?
absolutely nothing special and just flip it upside down. As you can see, this is really slow because the air bubbles have to go in to fill the vacuum that's created as the water's leaving, and these bubbles obstruct the flow of water. By the time the bottle was completely empty in this method, it was around 15.5 seconds. The second strategy is to swing the bottle around to create a vortex. As you can see, this creates a channel of air that helps relieve the pressure and improve the time. This method was almost twice as fast as the first one at around 8.5 seconds.
That's how you faster.
Lastly, the pro strategy, which is to use a straw, unblock the hole right as you release it. The straw provides a passageway to relieve the pressure, and it results in the fastest time at around 4.5
That's 4.5 seconds. So there, in case you want to empty the water tank next time, that's the fastest way to do. The next time when you go to some competition, there's a cool drink, and you and your friend decide like who will drink more. You know what to do. Yeah, that's about the siphon there, but siphon, there's one issue there. It doesn't work under a certain condition. If you look at the 0.3 now, if you apply your Bernoulli between 2 and 3, P2 plus rho G H2 plus half rho V2 square. P3 rho G H3 plus half rho V3 square. V2 is equal to V3 because the area is same. You end up with P naught plus rho G H2. This would be P3 plus rho 3 H3. So we get P3 will be P naught plus rho minus rho G H3 minus H2. Now we know pressure should be always greater than equal to 0. So H3 minus H2 must be less than equal to P naught by rho G. And when you calculate this thing comes to around 10 meters for water. This thing, right, we noticed it in barometer, remember? 10 meters of water column will balance 1 atmosphere pressure. That means, imagine you make a siphon like this thing. You make a very tall siphon like this. And then you try to bring it down. So you are creating a problem here. If this height becomes, let's say, 11 meters, now we know an atmosphere pressure can balance only how much? 10 meters of water column. So the water will never reach the top. Even if you create perfect vacuum here, the water will not exceed more than 10 meters. So siphon will not work. Are you clear with this? But in reality, you don't need actually 10 meters. It won't work even if the height exceeds around 5-6 meters also. So that is one condition you have to take care. So the difference between the highest point and the opening cannot exceed 10 meters. And the H1 must be always greater than H2 for the liquid to flow. Under these two conditions, the siphon will work. Clear with this? Clear with the siphon? There, that is the 4 concepts there. One is your what do you call velocity of efflux. Then you have your Magnus effect. Then you have your siphon and venturi meter. Only 5 meter, not 10 meter in real life. And because in real life you have surface tension, friction, all that stuff. God, so it doesn't work that way exactly. Clear with this. So with that, we are done with fluid statics and dynamics. The next part, viscosity. We will just do a little introduction today. Viscosity is again quite a small chapter. So what is viscosity? So till now we dealt with ideal fluids where there was no friction. In case of solids, we call it friction. In case of fluids, we call it viscosity. So what is viscosity? So there is an opposition to the relative velocity between the layers of the fluid. This property is called viscosity, and the force responsible is called viscous force. So just like solids, right? When two solid surfaces are in contact, there's a friction between them. So in solids, this is friction. Now, few things here. You have to remember these theoretical questions. If you increase the temperature, what happens with viscosity? If you increase the temperature, in case of liquids, viscosity of liquids actually decreases. Means a hot liquid will flow faster than a slow liquid. So when you're not keeping well, you get a fever. Fever is a symptom. Fever is not sickness. So what the body is trying to do by increasing the temperature of the body, your blood becomes less viscous. So your heart has to do less work. So in a way, it is a body's mechanism to conserve energy. Getting it? Some people think, if you increase temperature, bacteria will die. Bacteria will not die at 40 degrees temperature. Isn't it? If you increase your body temperature to 40 degrees, bacteria doesn't die. So you have to boil it to 80, 100 degrees. So this is one other thing. So what exactly happens here? The bond distances increase. So when you are heating up, the liquid's molecules will start vibrating. The distance between them will increase. So the interaction between them will decrease. So liquid flows much faster. But if you take gases, the viscosity of gases will increase. A hot gas will have more friction than a cold gas. A hot liquid will flow more easier than a cold liquid. What is the reason here? Now, in case of a gas molecules, they're already very far. Getting it? Now, when you increase the temperature, these molecules will start colliding more rapidly. We will see this in thermodynamics KTG. So molecular collision rate increases, which leads to more interaction. So the molecules which are generally very far, because of more collisions, they started interacting more. Now, viscosity is a very small chapter. We have only three concepts here: Newton's law of viscosity, Poisson's equation, and Stokes' law. So the first thing, Newton's law of viscosity. But any doubts on page 1? And definitely remember them. This is a good PYQ. Matlab, you can expect this in some exam, BETS or CET or mains or something. Today, your seniors' mains dates have come out. Most of them got on 21, 22, and 23, first 3 days. Now we will know the center after 3 days. Next year, it is your turn this time. Yesterday, we had a speed test for them. Every week, we're having a speed test. Till now, they wrote 8. I think the recent speed test, the test is for 1 hour, 100 questions, full syllabus physics. The highest was 93 correct, 100 attempted. And there are more than 80 people who did more than 85 questions. It was nice. The first speed test, people were struggling to do even 50. So they improved within that 8 weeks. People got used to, I think, that speed thing now. So what is this thing exactly?
So,
So
like, are the questions
you have a
easy
liquid.
in speed test?
Yeah.
So, are the questions easy in speed test?
They're a little easier than mains level. The point is not to give the tough questions. It is to make you select questions and get the formulas oriented. वो बोलते हैं ना, people will say ना, mug up the formulas. Instead of formulas, there is a better way to remember stuff. When was the last time you did 100 questions in 1 hour? That to full syllabus. That revises a lot. Till now, they wrote 8 speed tests. Matlab, we solved almost 700 to 800 questions. Other than the revision. In the revision, I think so far we did another 450 questions. So revision is still going on. We'll wrap up revision next Monday for them. So mains revision will get over. Then we'll do advanced revision in March. So if you have a plate like this, the area is A and the velocity is going this way. Let the depth of the lake be Z. Now the viscous force will be acting backward, F viscous. The friction will be dragging this plate from going forward. So this viscous force is given by, now it's all experimental. F viscous is given by minus eta A dV by dz. You should remember the formula. This is Newton's law of viscosity. So this Newton is there everywhere. We have Newton's laws of motion, Newton's law of gravitation, Newton's Lens formula, Newton's law of cooling in thermodynamics, Newton's corpuscular theory. Yeah, bolo na.
So like he had to give this law separately, like his 3 laws couldn't like explain this, or is it the same extension?
Not sure exactly. But this guy was giving so many laws, people were pissed off. I think they must have killed him because of that. So sometimes I get a feeling like this guy must be like, either a time traveler who copied everything and just started publishing. Right? No, but I think that's what happens, when you don't have internet, Instagram, PUBG, right? What do? You just sit there and start creating laws out of everything. So that's what happens. But Newton, right, most of his work, he did everything before he turned 30. After 30, he kind of became a nuisance actually. So when Newton died, they sold off all his papers and research papers. People spent a lot of money and brought it thinking he must be doing something interesting. At the end of his life, this guy was working on alchemy. He left complete science. He started working on alchemy, where he was trying to convert lead into gold. So not sure exactly what he was doing. He was doing all shit science basically at the end.
Too smart.
I think maybe he got bored, I guess. Like I said, I finished. He must be a time traveler. He must have taken HCV book and must have gone back. And HCV जैसा publish कर लिया. And book खत्म हो गया था. अब क्या करना है idea नहीं है. He must be doing something. But anyway, we never know. So what does this negative sign indicate? But right, that entire story is bogus actually. The place where Newton stayed, there are no apple trees. There was nothing like that stupid inspiration. Apple tree came and fell on his head and then he suddenly got an inspiration. Then he should have sat under a coconut tree. Completely, he would have gone only, permanently. Right? So it's not like that. So during that time, right, when Newton was studying in the university, there was a plague, just like our COVID ka thing. So they gave holidays and said, boss, please don't die in the hostel. You go home and die there. So they sent all the students away. So Newton came to his hometown. He was staying there and this guy was working on this gravity from long time, for months. It's not like suddenly he got an inspiration. But people like to make it dramatic, right? Like the way we make in our movies, no? And now if a villain is coming, hero is there. If the villain comes and beats the hero and goes off, there's nothing fun. So first you have to beat the villain. Villain will fall down. Then the heroine will cry. Then one drop of blood will go and fall on his face. And then he will get up. And so kind of, we need to make the dramatic thing. So I think they made that with the Newton also. But Newton was smart in that way. He's a pretty good, he knew how to deal with people. There were people who are much better in science than him. Think about this Galileo and all these people, right, who said, heliocentric theory, that the earth is going around the sun. The church actually punished them. Galileo was actually kept in jail. And after he accepted, no, boss, what Bible said was right, they left him. So in that sense, Newton was smart. Newton, you know what he did? Once he got all his theory done, he went to the church directly. Newton was actually one of the high clergy member in the church. He's in a very important position. He called up all the people. He explained the whole theory, and then he says in the end, "This is the language of God. I am trying to, understand our Lord's, what he called miracles and understandings through science." He never denied God. What people used to do, they used to deny this is all science, there is no God, and the church used to get pissed off and used to kill him. And this guy goes and says, "This is the language of God. This proves God exists." And the church people were like, "Awesome, Newton, do whatever you want. We are there with you." So just because you're right, it doesn't mean you should say it out. You have to present it properly. If you can do a proper presentation, you can even sell bullshit. And in US, there's a company which actually sells bullshit. You should search bullshit.com. There's a company. So what the company does, right? Let's say you have a friend and you really have a big grudge on them. You can go to that company website. You can put your friend address and you can order different kind of bullshits. They have different options. You have fresh bullshit. You have a bullshit which is fermented for a month, more smelly bullshit, right? You have cow bullshit. You have pikka shit and all the stuff. They sell all different things. So once you order that, they put it in a very beautiful box, awesome package. When you see that package, you will think definitely there is something awesome inside. And they send it to your friend's house. Right? They charge you for that bullshit and the box and everything. They make good profit and they'll make it anonymous. So once the package reaches there, your friend will get excited thinking, "Wow, what is this so colorful?" And you open it and you get bullshit inside. And the guy who made up that company earned more than $1 million. It's a very profitable company. I think it still exists. You should search. So if you can package things properly, you can even sell bullshit that is actually real. Anyways, let's see. So here the negative sign indicates velocity is the area of contact. This quantity, right, eta is called coefficient of viscosity. Now here you have to be careful. Viscosity eta ka units are poise. Now unfortunately this is a CGS unit. So one SI unit is 10 poise. Now, there have been questions on this and people did goof up. That means, example, in the question, if they give you eta is equal to 60 poise, while solving the problem, use eta is equal to 6 because that's your SI unit. So just be careful with that. If you don't care about that, you'll get an answer में 10 power में they'll get one error. So one unit is an SI unit is 10 poise. And you will notice there's a quantity called dV by dz. So dV by dz, this is called velocity gradient. Anything that changes with position is called gradient. Now for thin layers, if you take the liquid to be a very thin layer, you can approximately say dV by dz becomes delta V by delta Z, which is relative velocity between two layers. So when the liquid is flowing, different layers have different speeds. By distance between the layers. We will see more problems on this in the next class. We really don't have too many models on this. So this would be something like V2 minus V1 by Z2 minus Z1. This is only valid for thin layers. So just be careful with this. Clear with this? So that's your Newton's law of viscosity. So next class when we catch up, we'll continue from here. I'll show you more examples on this and we'll do some more problems on this. But it's a very small chapter. I think next class we will finish off next class. I think 1.5 class we'll wrap it up maybe. And then we'll start off with surface tension. Okay, with that, we'll wrap up for the day. Fluid mechanics is over, so please start working on that. And do remember there's a test online till tomorrow. Make sure to give it. So any doubts, anything else, please stay back. I'll see you guys again next week, same time. So take